from here we can construct group operators, how they act on functions, and based on that, if we have a function space with function basis, then using that we created representation. Okay, this is quite clear. Now what we will do is we will look at a very interesting example of a group called as permutation group. Now this group is going to be very interesting, and I'm going to relate permutation group represented by S3. I'm going to relate it to our group C3. So do you remember what the group C3 was, or C3V maybe? Yeah, the entire group. So I'm going to relate it with that. Okay, so let's see. So permutation group means what happens is, say, consider you have numbers, say 1, 2, 3, and you send the numbers to some different numbers, sigma 1, sigma 2, sigma 3. This is just a representation. What does it mean? Say for example, when you act the permutation group group element on a on this number, say 1 goes to 2, 2 goes to 3, and 3 goes to 1. This is a possibility. Okay, so what permutation element does? So if you have numbers 1, 2, 3, and if you apply a operator that permutes these numbers they go to different set of numbers, 2, 3, 1. Okay, so permutation group contains all those elements that do permutation of numbers. Okay, so for example, let me form a group. Okay, and this group will have 6 elements, and let's see. And now why 6 elements? If you have 3 objects, 1, 2, 3, how many possible permutations are possible? The number of permutations are possible is 3 factorial. So we'll have 6 elements in total. This is a known fact. Okay, so to consider all the permutations of 1, 2, 3, we at least need 6 elements to complete it. Thus 6 operators needs to be defined. So let's define. Let the first one be identity. So what identity does? It takes the element 1, 2, 3 and sends them to 1, 2, 3. This is the nature of identity. Okay, now let's define R. Remember, R was rotation in our previous case, and here in permutation case, if we define R as an operator that takes 1, 2, 3 to 2, 3, 1. Okay, and then now let me relate this R to our R we define in the equilateral triangle case. So consider this is our triangle 1, 2, and 3, and if we apply R operator on this triangle, what did we get? The 1 came here, 2 came here, and 3 came here. So as you can see, 1, 2, 3 goes to, so 1 is now in the place where there was 2. 2 is now in the place where there was 3. And 1 is there in the place where there is 1. You see, I have related the permutation R, permutation operator R here with the R operator that we defined in the equilateral triangle case. Okay. Similarly, let us define other operators. So W is equals to 1, 2, 3 goes to 3, 1, 2. We have sigma defined as when it acts on 1, 2, 3, it takes you to 1, 3, 2, and then sigma prime is such that it acts on 1, 2, 3 and takes you to 3, 2, 1. And then we have lastly sigma double prime that takes 1, 2, 3 to 2, 1, 3. So we know how these operators, when they act on this 1, 2, 3, so 1, 2, 3 can also be imagined as the name of the vertices of an equilateral triangle, and we know the result. Now the question is, what I'll do is I'm going to make it of this group element. By 3D representation, I mean that I'm going to make 3 cross 3 matrices that will represent the group elements. So let me start making them. Okay, so it is very easy to guess what will be the 3-dimensional representation of the element E. Of course, it is identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, can you guess what will be the 3D representation of R? So the matrix should be such that when it acts on 1, 2, 3, and what do we get? We get 2, 3, 1. So to bring 2, there should be 0 here, 0 here, and 1 here. And then, so this will bring my 2. Then to bring 3, I need 0, 0, 1, and then I need 1, 0, 0. Okay, so the matrix here is going to be 0, 1, 0, 0, 0, 1, 1, 0, 0 based on the definition. Similarly, you can make other matrices. So let's look at the 3D representation of sigma. Okay, so sigma was defined as it takes the element 1, 2, 3 to 1, 3, 2. So how the matrix is going to look like? So 1 goes to 1, so there will be 1, 0, 0. Then 2 goes to 3, so it should be 0, 1, 0, and then 1, 0, 0. And no, I made a mistake. So 1, 0, 0, and 2 goes to 3, so it should be 0, 0, 1, and then 3 goes to 2, then 0, 1, 0. So similarly, you can construct others. Now, why these matrices are a faithful or a good representation of our permutation group element is because again they satisfy this property. So if you have R and sigma, what did we get? R sigma gave us, I think, sigma prime. A quick check. R sigma sigma double prime, and sigma R gave us sigma prime. And so whatever relation is followed by these elements, we can check that the same relations are followed by the representation of the permutation group as 3 elements. Okay, now there is a very interesting thing. We also remember that there was a 2-dimensional representation. That means there was a representation that had 2 cross 2 matrices. If you remember, it had elements like √3, so on and so on, right? So there is a close relation between S3 and C3. So these two group elements are very closely related in terms of operation, and both the groups have a 2D representation by which the group elements are represented by 2 cross 2 matrices, and they have a 3-dimensional representation where the group elements are linked with 3 cross 3 matrices. That was quite interesting that I wanted to say here. So next thing is I'm going to talk about one more group just for fun. Consider a group that contains elements like A0, A1 that is only A, A2 means A square, dot 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 dot, A n. Now my question is, if this is a set with elements A square, A0, under what condition this set of element is going to form a group? Okay, we know that a group should have identity. So condition number 1 is A to the power 0 should be identity E. That means any A multiplied with the identity actually gives us A. Then there is another interesting thing is, if I need to do one more thing, I need to do A to the power n also equal to E. If I do this, then I should have actually n minus 1 elements here. So there should be n minus 1 elements. So if I do this, then let us check that this form a group. How about multiplication of A square and A cube? It will contain A5. Yes, it belongs to the group G. Well, let me denote it by G. How about A1 multiplied with A to the power n minus 2? Then we are going to have A to the power n minus 1. Then we will have A to the power n and A to the power n is identity. We are going to have A and A belongs to G. Yes. Similarly, you can check that all the properties of the group are followed. So this is just an example. Similarly, we can, this is a general example. I can, from this example, write a group of order 2. By group of order 2, I mean n is going to be 2. So it will have elements E, A and A square, and this will form a group when A square is equals to A cube is equals to E, I think. Now A square is equals to E, and then it will have only, yes, it won't have this element. So there will be 2 elements, E and A. Okay. So we can check that this is a group because we know that E and A will multiply to give us A, and we can say that A multiplied with itself will give us A square, which by definition is E, also contained in the group G. Okay. Now this was very important because I wanted to show you why identity element is very much important to have a group. Without the presence of identity element, a group is not possible. Now another example of what is not a group. So consider a set of positive integers. Can a set of positive integers form a group under multiplication? So the operation that I take is multiplication. The answer will be no. Why? Because consider an element 2 from the set of positive integers. We know that there should be an inverse, and the inverse is 2 inverse. Only then we are going to get an identity, but this does not belong to the set of positive integer. That means the inverse of the element which is required under multiplication, they don't exist in the set of integers. Thus, set of integers do not form a group under multiplication. Now the scenario will change depending upon whether you take multiplication as your group operation or addition as your group operation, etc. Okay, so this thing is clear. Next point that I would like to teach you here is, yeah, just a minute. Okay, now so let's go to the next page. Now I want to prove it to you. I want to prove that if group elements they are group, I mean the elements they form a group under a particular operation, then I'm going to prove it to you that there are, for example, T and S, let these be two group elements. So what happens? So when you have S and T, so if you multiply these two group elements, remember these are map that acts on something. So these are operators. Okay. So operators with some operation defined in them, maybe multiplication or something. So when you multiply S and T, you get another operator C, and it should belong to the group G. Right. So I'm going to prove it to you that if I have the corresponding operator OS, okay, so now this OS will act on the function space. So here these acted on coordinates and these will act on functions. So I'm going to show that OS and OT, they also satisfy this operation. So finally when you have two operators multiplied in this way, you'll get an operator OST, which will be equal to O of, I can write C. That means the once you make the operators out of group elements, I'm going to prove that they also satisfy the same relation as the group elements. So what is the aim? The aim is that we need to prove that operators satisfy same relation as the group elements. Okay, so how to prove this? Now what I'm going to tell you here is going to be very important for you because you will encounter this when you study higher physics book. Okay, now consider there is this group element T such that when T acts on the coordinate X, say you get X prime. Okay, so if you are on one dimension, then say this is point X, and when you operate T on this point X, you go to a new point which is X prime. Okay, so we are doing everything in 1D. Now when you're going from one coordinate to another coordinate, I can define a operator OT which acts on the function space such that when OT acts on any function which is a function of X, this should give me a different function. Okay, let me not write it like this. I will do so. It should give me a different function, psi prime. Okay, so there is T which acts on coordinate, gives me new coordinate, and its corresponding operator in function space, it acts on functions and give a new function. Okay, now the question is, how can we relate these things in a more understandable way? What I want here is, I want that whatever a function is, when it acts on psi of X, say we get some value 8, just a random value. X is some, say maybe X is equals to a 2. So there is some function at point 2 you get 8. What I want is If I act the same function on a different point, then I will not get 8. Yes, so consider x is 2 and x prime is x plus 2. That means this element t, when it acts on x, it takes you to x plus 2. So what is x prime? 2 plus 2, 4. So now you are at 4, and the question is, if you make psi as a function of 4, psi depend on 4, are you going to get 8? Answer is no. Let me give an example. Consider psi of x is x cubed. So when x is 2, psi of x turns out to be 8, right? But if you say that I'm going to act psi at x prime, then this would mean x prime cubed. And what is x prime? It is 2 plus 2 is 4 cubed, and I don't get 8. So if I want 8 at the new point x prime, then the structure of my function should change, or I should say the form of my function should change. So let the new function be x prime, and x prime takes value at psi prime. So new function is psi prime, and psi prime takes value at x prime such that its value is equal to what psi had at x. Let me give an example. So here psi prime can be maybe 2x, I think. I hope it will work. So let's see if psi prime is of form like this, does it work or not? So let us calculate psi prime of x prime, that is 2x prime, where x prime needs to be substituted 4, and you get 2 into 4, which is 8. Yes, so now everything is fine. So what I want to say here is that if you are on, say, 1D, and if you are at a particular point x, and if I take you to a new point x prime, then if there was a function which acted on x and gave you some value, to get the same value at x prime, the form of the function needs to change. Only then you can equate them. I hope you understood this. Okay, so now what I can do is, I'll say that psi of x is equals to the operator acting on psi at x prime, that equals to operator that equals to psi prime of x prime. I want you to understand this one carefully. What happened here if I do such kind of definition? So you see that the transformed function psi prime takes the same value at the image point x prime here. What is image point? So t acted on x, and whatever you get after the t acts on x, this is called as image point. Okay, so the transformed function psi prime takes the same value at the image point x prime that the original function psi had at the object point x. So x has the name object point. So that's the original plan. Okay, so this is how the operator, this is how t and this is how ot they act. This is how they act. So this is the thing that I wanted to tell you, how t and ot should act. So t takes you from one point to another point, and OT acts on the function to give you a new function such that at the new position. So OT gives you a new function at the new position. Okay. So this is just one part that you need to remember. All you need to remember from now is only this. Forget everything what I taught you. Just remember this. Now remember what is our aim. Our aim is to show that the operators, they satisfy the same relation as the group elements. Okay, so this is our aim. So let's fulfill our aim. So now, as you have seen that T takes x prime, which is equals to x plus a. So T translates x. So, or I can say T of x is x prime. Okay. Can I write this? Psi prime of x is equals to psi of x minus a. Can I write like this? Yes, I can write like this also. Okay. Okay, this is just aside. Now, main point. So, how does your OT acts? So, when OT acts on psi, which is a function of x prime, it is equal to psi of x. That implies when OT acts on psi, because we know that when this OT acts on psi, we get psi prime. So that you need to keep in mind. And what is x prime? X prime is nothing but T acting on x. That implies I can have OT acting on psi of x when psi, and here we have T inverse x. And this is similar to this. Okay, I hope this point is clear. Now this is one function. Let me define another function. Consider that function is OS, and what S does, so when S acts on x prime, it takes you to a new point x double prime. Okay, so what OS can do, so OS takes psi, and what should I have here? I should have x double prime is equal to psi x prime. Okay, this was similar to what? Similar to OT acting on psi, a new point is equals to psi at old point. The same relation I have written. If you look at this, x prime was the old point, just like x was, and x double prime is a new point, just like x prime was. Okay, so this is how I define OS. So if you look at OS carefully, then I can do the following thing. I can say that OS okay, let me do one thing. Let this be prime and this be double prime. Okay, because we are going from, so we went from psi to psi prime, and now we are going from psi prime to psi double prime. So accordingly, in the coordinate space, we went from x to x prime through t, and through s we are going to x double prime. Okay, similarly we went from psi to psi prime and then to psi double prime. So here we used OT, and here we are going to use OS. So OS on, I can write psi prime, and this was x double prime is equals psi prime x prime. Let me remind you again why I wrote this. Remember OT? So OT acts on old psi. Okay, look at the chain. So for T, psi is old and psi prime is new, and for S, psi prime is old and psi double prime is new. So for OT, when I wrote psi, psi was old, but the old was acted upon at the new point x prime. Here the new point is x double prime equals, then you have the old psi acted on at the old point. Okay, so here the old psi is psi prime and the old point is x double prime. Okay, so this is easy. So let us look at the behavior of OS. So I can do one interesting thing here. I know that I can write OS, but what is psi prime? I know that psi prime is when OT acts on psi. And what is x double prime? I know x double prime is when S acts on x prime. And this side, what do we have? We have psi prime x prime. And I already proved that psi prime x prime was psi of x. Now you look at this interesting structure that I'm getting. I'm getting multiplication of two operators through this definition. So what do I have? So I can write OS, OT, psi of, now this thing can be written as ST of x, which is easy because we know that x prime is Tx, and just write this side as it is. So what do we understand from here? So let's see, this is an important thing that you need to remember. Okay, so we understood that you can redefine the entire thing here as a new operator OST, which is a combination of OS and OT, which acts on psi of STX, and it takes the same value at psi of x. That means that OS and OT, they actually combine to give you OST, a new operator, and the whole thing, they belong to the same group or set. Just like your if you have S and you have T, if you multiply them, whatever you'll get ST, which in short form I wrote C, that it belongs to the same group, right? And if you look at them carefully, the multiplication thing is properly taken care of. Similarly, the operator also behave in the same way. This also means something else. This also means that if I do the matrix representation of S, and I will do the matrix multiplication of T, and if I multiply them, then I'll get matrix multiplication of ST. That is, if S and T, they multiply to give me a operator C, then to get the matrix representation of C, all I have to do is I have to multiply the matrix representation of S and matrix representation of T. So even the matrix representation, they satisfy the same relation as the group element. So hence our aim is fulfilled. Is this clear?
Yes.
This is quite confusing. If you go through the derivation one more time from top to bottom, things will be clear. Okay. Now let me give you an example. We already did this example, so I'm going to come one more time. So the example was, okay, let me write the relation. So psi prime x prime is equals to some operator, say T, acting on psi x prime is equals to psi of x. So the whole idea is whatever the value of a function at the old coordinate has been taken to the value at the new coordinate by a redefinition of a function. So we have to define a new functional form. Okay. Now if you look at an element, remember we worked with an element E and I, and I formed the matrix representation of E and I. So what was E? E when acted on X gave me X, and I when acted on X gave me minus X. And previously we used two bases, psi of X and psi of minus x, and using this basis I created the matrix representation of E and I. Remember? So now if E of x is equals to x, okay, then how the operator version of E, which is OE, how it acts on the function space. Okay, let's take a quick look. So the idea is the following. So write the whole thing here. Psi of x prime is equals to OE psi of x prime is equals to psi of x. Okay, I just wrote it and I replaced the operator OT with OE. Now let us see that if there is OE here, what changes I can make. Now since OE, it acts on the x prime. What is x prime? Fortunately, x prime is equal to x, because E is the group element that is an identity, that it takes you from the same element to the same element. So when x prime is equals to x, and this is psi of x, then if this point is also x, then you don't need to change the form of the function. So psi prime will not change. So I can just easily write psi. And hence I used this relation to make the representation. Let us look at OT. Okay, write the entire stuff again. Psi prime x prime is equals to OT psi of x prime is equals to psi of x. Now if you look carefully, OT psi, but this is minus x. Okay, so the new coordinate was minus x. So if you are at minus x, then what should you have at this point? You should have what? Any guesses? Of course, you'll get psi of you should get psi of x. Yeah, you should get psi of x. Is it clear? Just take a look again. I hope when you do it, it will be clear. So and we used this relation and we formed the matrix representation. So this was an example of how to use this thing, this part. Okay, so anyways, so this thing is clear. So now we are going to do a new thing, and the new thing is the following. We are going to learn how to add a representation. So this is something very interesting. Addition of representation. Okay, so this we will do in a new class. So what you do is cut the video right now, and after 5 minutes we meet and then you start the video recording. Okay, so we meet in 5 minutes.
Goodbye.